Hello, everyone. A very good evening to everyone. So, I'm Aishwarya Shuru from Altum Technologies, and thank you for joining us on this session. So, this is a session from Altum Technologies along with Cellink. A quick introduction myself. I am Aishwarya again. I'm a technical specialist at Altum, and I'm dealing with the whole sector of 3D bioprinting at the moment. So before I go down to this new session that we have, which is the advances in bone and cartilage substitutes, I'd also like to tell you about what was the previous set of sessions that we had carried about. So the first one was say precision medicine and knowing what 3D printing is. From there, we jump down to understanding materials, understanding the printing of skin, and now we're going down to bone printing. So I'll just share my screen right now so that you all can see the presentation, and I'll start with the topic. So I hope you can see my screen. So today's topic is going to be the advances in bone cartilage substitutes through bioprinting. Again, 3D bioprinting being the word. A quick introduction about us. We are a 3D innovation platform company, and like I've already said before, we have quite a lot of solutions on us. So we work with Dassault Systems, CATIA, we work with MSC software, we work with Stratasys, Artec 3D, then Biovia, Life Sciences Simulation, and Cellink. So what we are is in fact in areas of healthcare, in areas of life sciences, in areas of automotive and mechanical and mass production, and that's where our solutions come into use, and it quite helps a lot of people. So we were established sometime in 2011, and we've been setting up foot since then, and establishing recognition, and making more and more progress. And now we are adding up more products, working with more set of clients, and we have a growing set of customers, clients that work with us, and they range from say education and research, aero and defense, automotive suppliers, others, healthcare, IT services, any sort of OEM. So you name it, we work with most of these institutes. We work with healthcare centers and even life sciences solutions. So with life sciences, we've had an initial work with our Biovia system, and now we're also part of the selling team. So that's why we also have a different set of foot in the industry. So like I've already said this before, that if you think that this is just limited to life sciences, no, we are a solution for almost everything, every problem. So you can always visit us on Altum Technologies to check out our website to see the products that we have, the solutions that we've created. And in case you need any sort of help, any services required for your research work or any sort of work, we're always there to help you. So I start with the topic, which is what is bone defects, because the idea here is to create artificial bone or create something similar to the bone, right? So bone defects is actually considered as a lack of bone tissue in a body area, where the bone should actually be in a certain shape, size, or in general terms called normal. So you will have bone defects occurring due to several congenital or acquired conditions. So maybe it can be trauma, it can be age related diseases, um, it can be a disease acquired over time. It was something you would have already born with. So all of these bone defects that exist require a solution in terms of functionality, movement, as well as for aesthetic reasons. So there are several types of issues that happen, or certain types of traumas that occur when it comes to bone. Say you have a fracture, or you have any sort of a large shatter, or even a hairline, or even a heavy fracture that can happen to your bone, maybe any part of your body, or it may be a disease like osteoarthritis, or it can be any sort of maxillofacial defect that can be either congenital as well as something that has happened due to, say, post surgery, like in the sense if you have had a situation of cancer treatment, cancer removal, tumor removal, or even in the case right now where we talk about COVID-19. So the black fungus case where people have lost their jaws and their nasal sections, and that's where it was quite fatal, and people have had to lose a lot in that process. So having this field of medical devices and medical innovation actually helps in replacing and helping you out in taking care of these issues. So when you talk of maxillofacial defects, you'll always have many sets of solutions that are available. Like the maxillofacial defects, you also have very basic, small maxillofacial surgeries, maybe um, um, orthotic or dental removal, or any sort of periodontitis sort of issues. So you have different types of issues which can reflect when it comes to bone defects. And in fact, you'll also have cartilage defects, maybe with the nose, maybe the ear, maybe your knee. So you have several types of bone related issues that actually occur. And there is a lot of research, a lot of work, a lot of solutions also being provided when it comes to having to take care of this. So in the case of medicine and healthcare, initially when it came to maybe fractures or bones, we would go with using rods. So basically beams and rods were the solutions, where you would have the broken bone supported with another rod like structure, which would act as a whole load bearing, shear stress and shear strain sort of a distribution. So it can in fact hold the load, also distribute the load. So that was the whole idea. So it requires a lot of mechanics when it comes to considering bone, because again the skeletal system is the one which gives the whole structure to the body. So if we have the bone quite intact or in its right form, then it gives the function of protection, it gives the function of providing structure, and also covering most internal organs in our body, right? So when we talk of the initial set of work that was done, or how we had initially looked at taking care of trauma or any sort of bone deformity, has been through surgery. And the effect or the conventional results that come out may or may not be positive. There'll always be some sort of comorbidity at a side. There might be some sort of problem. Replacing a bone from one part of the body to the other again will have a problem. So you have implants and grafts that have been created. So the solution that you see right now can be done with your conventional methods, that is just creating your basic titanium implants, or creating your rod like structures, which are something which is, you would say, not entirely customized. So they're present in standard forms, which is not actually relevant when it comes to each person's body. Every person's structure is very different. So that's where 3D printing came into picture. Again, I quote 3D printing. So 3D printing was just creating layer by layer structures using our basic materials, may it be polymer, plastics, or it could be metals. So when you talk about any sort of issue, right, you will see that they have 3D printed maybe, or created any sort of ball and socket sort of uh, structures, maybe the spine structures, any sort of maxillofacial structure. You would have your bone, you would have general prostheses. So many such forms that are actually created, and these tend to provide the required form, function, fit, as well as also be biocompatible in nature. So if you're using materials of a certain kind, like you're using titanium, to some extent you use coated stainless steel, you also use certain type of polymeric materials, peak material. So there are many categories of materials you could use, and I think I have mentioned this in my previous session about biomaterials, right? So these 3D printed forms are used in replacing or in adding up to our existing bone structures to aid in terms of any sort of deformities caused. So 3D printed parts are one thing, and when you talk of the solution of 3D printing, it will always involve imaging, taking the image of the patient itself. So you have quite a lot of customization, and it is more specific to a patient. It's more precise. And with these images that are formed, you actually convert them into a 3D design, and then you would again go about with the normal process of printing, except using materials like polymers, plastics, metals. So while you also have 3D printing being used for just in the form of grafts and implants, you would also use 3D printing in creating something called surgical guides. So, surgical guides help the surgeons across to allow better accessibility at the site where you need to undergo the surgery, where you need to do the main work involved. So, 3D printing itself generally can add that feature of allowing, using surgical guides, which can really shorten the time, improve the lifespan, improve the time involved to carry out the surgery, and also give you better results. So this is a small video, again something from our own work with statuses and altum, showing you how the surgical guide works. So you would see that they have actually attached it at that site where the bone is, and they are able to do better cutting precision with the help of these guides. So this will really help them to hold things together and carry out the surgical process. So again, our idea, our whole aim is 3D bioprinting, which is using biological samples. And like I've said before, we are going to use the principle of tissue engineering itself. So again, 3D bioprinting is going to be a classic definition for us. So it's a form of additive manufacturing which are using cells and other biocompatible materials as inks to print living structures layer by layer, and the idea is to mimic the behavior of natural living systems. So when you're talking about 3D bioprinting in terms of bone or cartilage, you may or may not use cells themselves, or you can just use materials which are more biocompatible, more easily available in terms of creating the slurry type or any sort of uh, material basically. So you are trying to optimize materials and create materials which can really help in creating your bone structures. And like I've said, we have used the idea of 3D printing again. Along with that, we have tissue engineering being incorporated, and the essence of this is going to be cells, bioinks, and culture media. So when it comes to bones, the cells that we would usually go about with, I mean, the required cell for bone is the osteoblasts and the osteocytes. So we would use MSCs in that case, which are mesenchymal stem cells. So mesenchymal stem cells are again human, isolated sort of bone marrow isolated stem cells, and these stem cells have the capability of differentiating to form the required set of cells. So mesenchymal stem cells can differentiate to adipocytes, osteogenic, and also another form. So you have several types of programmable. When you say programmable, you're using growth medias and culture medias to actually carry out that process of doing the printing, and this will allow in creating your bone structure. So steps involved are again going to be, as we have already done them. They would be 3D scan, anatomical data, MRI scan, so imaging again, followed by 3D design. Then we have material selection. We have cell selection, which clearly is going to be bone cells for us. Bioink development, extrusion or DLP based printing, which is the method we would want to incorporate in terms of printing. So extrusion based printing is a method wherein you are going to extrude a certain type of object, a certain type of material through a system, a pneumatic based system or an inkjet based system or any other system, to create this layer by layer fashion. And DLP printing is again using light assisted printing. So here you're using light in order to print a certain type of structure using your projected light, which can give you better and more precise design when it comes to creating maybe bone or maybe any other form of structure. Then you have cross linking, where you have curing, incubation, maturation, and in vitro test and application. So when it comes down to bone, it's such that when you're printing with bone, basically MSCs, you would print it with a material which can give you something as close to the rigidity of bone. And it's actually not very easy, because we are trying to create a sort of bone structure which can be rigid, which can give you the mechanical capabilities, and can also allow in a sort of high shape fidelity and also better retention. So UV curing is very important here, because you're trying to create a more mechanically stable structure. Incubation being another phase, and during the incubation phase, you also will come across a point where you need to do the differentiation of the cells. So the differentiation here would require using specific growth medias, which will actually enable the differentiation of mesenchymal stem cells into osteogenic or osteoblast, osteocyte kind of cells. Um, so here you have the in vitro tests, right? So among the in vitro tests, it's very important to understand if my MSCs have actually differentiated into a bone, that is osteoblasts or osteocytes, and are they actually providing that sort of bone osteogenic formation? Will I also have induction and conduction of the bone tissues or the cells? So here you require some markers and some tests that involve in checking the calcium content, to see the alizarin tests, which is done exactly to see the calcium content, to see if there is a good amount of calcium deposition, good amount of ECM production. So these are essential when it comes to printing for bone. So again, I will go with cases now. Now these cases would be one. This is again one of my very interesting examples, which involves both 3D printing as well as 3D bioprinting techniques. So here you would have a case where if a patient has got a sort of deformity in this has been actually the radius ulna bone, which is present here, actually went through a fracture, and for that the doctor has tried to create a simple graft solution. And this is an actual in vivo case on a human, where they have tried to see the extensive impact of using specific biomaterials. So the materials that are generally used for bone grafts are maybe alginate, collagen, silk fibroin, gelatin. These are most widely used words. Then you have bioceramics like hydroxyapatite, tricalcium phosphate, biphasic calcium. So all these are there, and they're all in certain forms, say beads or coatings or injectable cements or whatever. And they're all available in the standard size and shape, and they need more processing time. So if you're talking about one particular patient, every person's deformity is going to be different. That's why they do the x-ray and they see whether this is the right shape, whether we can use this. So in some cases they also require CT scans and for the data acquisition, to get a precise model of what is the deformity exactly. So when you're using 3D printing, it will just help you make a perfect fit when it comes to any sort of deformity, any site of disease, so that you can replace that point with something artificial or something more closely biomimicking. So here they have used hydroxyapatite, and this has been mixed with thermoplastic materials to adjust the degradation time. So when you talk of hydroxyapatite or any other material that we have, they are all materials which can easily degrade. Since they're biocompatible materials and they're bioabsorbable materials, there are chances that these materials tend to degrade with the flow. Will leave out parts, and because of the amount of liquid flow within our body because of the amount of calcium, sodium, potassium, transfusion, you will also see that these kind of create a sort of reaction. Yes, the idea is to have that reaction to allow regeneration process, but it shouldn't degrade so fast. So that's why for most biocompatible materials, we try to add a more biocompatible thermoplastic material which can allow in adjusting the degradation time so that this bone structure retains in the body for longer so that it induces regeneration better. So you would use a CAD file again of specific dimension. First thing is you are first trying to see what material you want to use. Say when we have taken hydroxyapatite and thermoplastic material, we have formed that perfect blend between the two, but we also need to see what can provide the best infill. So when I talk about infill, it actually means that you're trying to create something which is more stable in its structure. There's better shape fidelity, as in there is better clarity in what's being created. If I'm trying to create a basic grid line, it has to be very clear, it has to be crisp when I've created it. So using infill is very essential because you also need to understand that whatever structures you create have to be mechanically tested and they have to take the load quite efficiently. So there are tests done, which is mechanical tests, load bearing tests, any other, maybe some analysis to an extent to understand the surface, the topology, etc. Um, so when you see among different infills, say 50, 75, 100%, you would choose which is the best one that is for that required application. So when you're taking this patient specific data, you're taking the patient CT scan, you're segmenting it. Basically, you're segmenting or taking off the part which needs to be replaced, where the graph needs to be added, and you're reconstructing the whole image. So the subtracted part, which is the segmented part, is going to be the essence of your CAD design. So that is the one which is going to be printed by your normal 3D printer as well as a 3D bioprinter. So in order to allow efficient uh, surgery, right, you need to carry out the surgery process. The doctor needs to understand this is the site or this is the point I need to go to, for which you require a pre-surgical model. So I have mentioned about pre-surgical models. So these are very effective when it comes to saving time for any sort of surgery. So having printed a plastic or a polymeric 3D printed model where you can easily understand the site where and from how you can attach the graft is easier. And then you can go down to the process of actually using your biomaterial, which is hydroxyapatite as well as a thermoplastic blend, being printed in a specific infill, having done or having gone through the tests, that is the optimizations required, maybe having the nozzle dimensions checked, the print speed checked, the material reproducibility, the reconstruction, and also it's very essential to understand the graft to defect distance. So if you're getting a good analysis of how you would uh, clearly put in your ceramic based material in that spot, you will understand how you can use that as a graft. So this is an actual case of using graft, that is a ceramic based graft material, which is more customizable in the case of a patient. So this is one of the examples I could give you initially in terms of using or creating biomaterials that can successfully be used in terms of bone grafts. The next case is highly tunable bioactive fibers. Again, bioactive fiber reinforced hydrogel. Now, this is for allowing guided bone regeneration. The case here is actually periodontitis. So here, what happens is your soft and hard tissue damages. So within your teeth, within that whole section of your lower jaw where the teeth lies, because of periodontitis, there is a sort of effect that causes damage to the gums as well as the underlying bone. So here they're trying to use a sort of fiber reinforcing material. So when we are talking of materials like say alginate, gelatin, etc., they are materials that tend to degrade. Like I've already said, they also lack so much of mechanical properties, so they require some sort of additional material. You need to make your biomaterial more smart in order to carry out the process required. So every time you design any bone structure, it is first important to see which part of your body you're going to use it. Also, it's very essential for you to understand what are the type of stresses it's going to experience. If I am talking about any deformity which is in my lower jaw and I have to make a graft material which is here, I need to know that whenever the patient, or in case of in vitro tests, in vivo tests or animal tests, you will know that there is a force which acts over here. So every section of your lower jaw has a different force that it experiences. So maybe here, because again you have your molars and premolars which do the main grinding and chewing. Then you have your canines. So each section of your lower jaw has a different stress. In fact, even your upper lip section. So when you're designing something, you have to understand that will this bony structure that I've created actually bear the load? Will it stay intact after, maybe a surgery or something? uh, so here we are trying to create a tunable material. So you are trying to take care of the mechanical competence as well as the therapeutical features by integrating maybe porous polycaprolactone material. So you've used polycaprolactone along with our basic materials, and you've tried to see whether um, your existing materials, say maybe alginate or gelatin material, which have been used. I think in this case you've used gelma material. They're also trying to blend in something else to allow the degradation time to be greater, to have better therapeutical features, to have better 3D architecture, and also see whether there is better fiber. So, adding, they have also added amorphous magnesium phosphate along with PCl. This is again to improve the mechanical properties and to improve the osteogenic ability. Now, osteogenic ability would be, when you talk of regeneration in very layman terms, it actually means that I am trying to bring something into my body which will allow the rest of my parts, maybe the bone, to allow regrowth better, right? So when you're adding any type of stem cell or any type of cell in that part, what that stem cell does is it creates these growth factors, create these signals which allows the neighboring materials, allow the neighboring cells to actually allow to function better. Because again, that's a point which is diseased, and there is no better connection between the two parts of the deformity. So you're trying to bridge that gap by creating some sort of graft like material or implant like material which is going to allow better growth. um, so you will actually look at guided bone regeneration as an idea, and after in fact printing the structure, they have also tried to do the in vivo tests, sorry, in terms of the rabbit jaw or the rabbit structure, to see whether they can efficiently see any sort of osteogenic differentiation. Also, having printed these materials, you have to also see whether the cells are more viable within them or not. So if they are viable, then there is better growth factors production. There is also a more sustainable bioproduct that you have created. Um, so there are similar such cases, like the next one being using graphene oxide as a material, right? So this is a case wherein you have 3D bioprinted graphene oxide cell laden bone mimicking scaffolds. Now this is for better scaffold fidelity, osteointegration. So bone realization is something which you will hear quite often when it comes to talking about bone 3D bioprinted scaffolds. So either you would print the structure along with the cells in it, or you would see the cells post printing. Um, so the problems or the cases, what you will see is that polymer based inks, they create a case of insufficient mechanical strength. There is low scaffold fidelity and a loss of osteogenic induction. Now that is because of intrinsic swelling and bioinert properties of most polymeric hydrogels. So That's the general case, and that's why we are trying to make things better. So they've used human mesenchymal stem cells along with graphene oxide, and you will have a blend of alginate and gelatin composites to form 3D bone mimicking scaffolds. So GO, which is graphene oxide, is a bioink material which is good in bioprinting, allows better scaffold fidelity, allows in better cell proliferation, osteogenic differentiation, and also ECM mineralization. So whenever you have any bioprinted part, the most important function of that is to provide ECM. So if it is provided a certain amount of maybe GAGs or the subsequent components required in the ECM, collagen, etc., then it has successfully done its job of at least incorporating or inducing better bone growth within the body. So again, the process is going to be as simple as finding the defect model, printing it, doing the process of cross-linking to allow better strength of the material, incubating, printing it, then doing the post-printing processes where you are going to keep it in an osteogenic media, that is basically an osteogenic differentiation medium. Then you would allow better growth of that, see whether there is good amount of mineralization or good amount of growth factor production. So there are some cases where they have been able to successfully do the bone printing to give you structures. Like example, even in case of spine, the spinal cord injuries, there have been certain studies where they've been able to efficiently or even closely create structures which can allow better connectivity among the bone cells, among the neurological or the neural cells. This is actually cartilage, and while we have dealt with bone, cartilage reconstruction is also something. So development of 3D cell printed structures and as an alternative to autologous cartilages. So whenever you have a lot of cartilage injuries or something, it's quite easy now that you can easily reconstruct or recreate autologous cartilages for auricular reconstruction. In this case, they have taken a rabbit model and they've tried to understand and assess the difference between an autologous cartilage, a 3D printed cartilage, a cell seeded cartilage, or even a bioprinted cartilage. So they're all very different from each other. Autologous cartilage being, the own part, which to see whether there is good amount of implant retention, whether there is a regeneration at that site. Next being a printed scaffold. And now this scaffold is something which will actually incorporate well, grow well, maybe provide enough structure, but it's possible that it might not have or might not produce the best regeneration. And then you have 3D bioprinter, that is printed with cells, right? So the idea of printing with cells is actually to allow better distribution of cells, to understand better porosity, to provide better mechanical strength, to allow better three-dimensional accessibility of cells, better interaction between cells, etc. And these structures in this case or in this study have been that they have tried to check the regeneration at the rabbit ear. So, upon comparison, the whole idea was to see whether there was good cell viability and whether there was a good regeneration of the cartilage. So, in the studies, they were able to understand whether using a specific scaffold or using a hybrid scaffold or so will give you better mechanical strength or not. So, in this case of hybrid scaffolds, they were seeing that there is a better tensile strength. So, it is able to take care of any loads which are falling, or even that own material itself has better mechanical strength in terms of retaining, in terms of going through any stretching, any other such thing. And you will also see that there is a greater number of cell viability, which I mentioned. And this is actually an image of the regenerated part using the 3D bioprinted structure. So there is less amount of scar tissue formation. There is a good amount of cartilage regeneration in that area. From again using these basic cartilage structures, you also have studies being done again from selling themselves, where they've tried to understand whether just using a basic structure will give you the good amount of function, or you can even use the actual anatomy and physiology to create something in future, to maybe see if there is a cartilage production, good amount of calcium production. So here they've taken a basic blueprint or a basic structure of the ear, and they have taken human nasal chondrocytes. So they've taken about 20 million cells. They've used the bioactive printer which we have, and to that they have added calcium chloride, which is a cross-linking agent, and they've also added some medias. And after proper maturation, they would see, the ear construct after 4 weeks in vitro. So upon studies, upon doing the evaluation at day 14 and day 28, you see that the agricin, the collagen 2, the matrilin 3, and COMP, these levels are either in some cases quite consistent or in some cases inconsistent. So you'll see that the GAG level, which is glucose aminoglycans, is very important in terms of the ECM production is high when it came to 28 days. So it gave a good understanding to see that cell-laden materials can actually provide a good housing or a good base for creating any sort of cartilage-like structure, and that can be in future incorporated when it comes to trying for cartilage printing. So, like I've also mentioned this before, and I think most of you know, 3D bioprinting is at its research phase. There have been points where it has been successful when it comes to printing, maybe without cells, using smart materials. Everyone is now progressing towards creating more artificial bone like structures and see the impact of using specific material, using specific cells, and using them at a specific site to see if they can really replace certain old methods. So another example I can give you is in terms of any sort of disease recovery. Like I mentioned about skin before, about wound healing, that way you will also have examples in terms of maybe maxillofacial defects, right? So you would have a scenario wherein there is an injury or a deformity at the maxillofacial section. um, you would also have to provide use materials which can be temporary materials um, before it going to any other process. So we are just trying to incorporate more regeneration when it comes to using cells and using biomaterials. So that's where you will extensively see a lot of work done using collagen, using alginate, using gelatin materials, hydroxyapatite as well. And while you're using these specific materials, there are also smart incorporations done, say using nanosilicates, using nanoparticles, or using thermoplastic materials, which will actually help in, better degrading, better stability, better mechanical incorporations, etc. And these will actually help in understanding better in terms of better treatment processes, better pre-surgical modeling, or anything of that sort. So like I said before, our products are incredible plus, biox 6, bio mdx, which is an industrial grade machine, luminex. So you can definitely see our previous sessions, our coming sessions, where we are going to tell you more about how bioprinting process works. You can see the working, the functionality, the processes, what you actually go about to do the bioprinting process. So from Cellink, we also have BioVia, which is a biological modeling and simulation suite where we have something called Discovery Studio, which is known for protein engineering, antibody modeling, simulations, predictive ADME toxicology, X-ray analysis. So BioVia is used extensively in the bioinformatics and the cheminformatics, and in terms of ideally, in terms of drug development, drug testing, etc. You can just join my colleague Divya's sessions to understand more about BioVia if you'd like to. You can always visit Altum Technologies, find us on the LinkedIn page, see our YouTube channel for our pre-existing videos, and thank you so much. Now we have this quiz that we've been carrying out for some time. So the question here for your quiz is actually, what is hard to achieve while mimicking bone? Color, shape, mechanical properties, topology. So here are the rules. You can answer in the comment section. Subscribe. Make sure that you're subscribed to our YouTube channel. Share this video or this whatever contents that we have on the social media platforms that you're available in. Tag a minimum of 2 friends to challenge them, and use these hashtags, hashtag selling, hashtag altum bioquiz, while sharing the post. So with our old set of questions and this session and the next coming up sessions, we will have 3 winners who we will select based on whether they have actually gone through these criteria, have done these, and the winners would get Amazon gift voucher worth 2000 rupees. So thank you so much, and thank you for patiently listening. So uh, I will see you again, and yeah, also we'll have a Q&A session for a while. So if you have any questions, you can you can easily come down and ask me those questions. Okay, so I will slowly take out the questions from the chat section. Just a second. Yeah, so this question by Niti Mehrotra. So she asks me what are the type of printers that we use for bio implants. So for bio implants, we usually use 3D printers, general titanium metallic 3D printers, and also to some extent we would use bio printers for maybe creating ceramic materials. So they follow extrusion printing. So for extrusion printing, they would use these types of materials to create bioceramic based materials or anything of that sort. And I hope this answers your question. I'll go to the next one. Okay, so um, Dipankar asks, can you use differentiated cells other than stem cells for this purpose? If no, why? So they actually do use, maybe in the case of bone, they use osteoblast cells, but getting or extracting these osteoblast cells are not very easy. You actually need to extract it from a bone tissue material, and availability of that could be there, but if you're trying to make it more specific, then it is hard. And I think using stem cells has more therapeutic effects, and you can easily program it because of its availability. Mesenchymal stem cells are quite easily available from bone marrow and few other sources. They are differentiated into maybe osteoblasts or adipocytes and etc. So that way they actually help in creating or being more available in terms of the research work that you want to do. So I hope this answers your question, Dipankar. The next question is, okay. Uh, if we produce alveoli lungs using bioprinting and biocell, is it effective? Okay, so you can't really get functional, absolutely functional models. These models are again in the phase where you're learning how the whole physiology, the anatomy of it works. So what you can essentially do is use it as a disease model to understand studies, or use it as a model to understand the whole physiology. But you can't just directly put it into your body. Like, we are not that far right now, because we are just dealing with very simple cells, right? Our human body consists of more complex set of cells, multicellular in nature. So understanding the co-culture nature of all the different types of cells and how they interact with each other will eventually allow us to incorporate this into the body and also consider the immunological factors. So, Raja Rajan, I hope this answers your question. And okay, all right. Yeah, I don't see. Okay, one second. Will the bone implant created the 3D printing break? Okay. So the bone implants created through 3D bioprinting, will it break or does it cause rust? So they try to use materials in case of general printing, maybe metal printing. They try to use materials like stainless steel, and they try to use materials like titanium, right? So these materials are known to cause less amount of rust. Always every metal has a time span which it can be in your body and how long you can sustain. So I can say that yes, there are chances of things breaking. This is exactly where the whole research idea is going towards, creating something which can't break so easily. That's why we're trying to blend in so many materials together to create something more mechanically stable. Another question: how useful is 3D bioprinting in treating jaw grafting? So there is a lot of work done where they have tried to create lower jaw implants, etc., using 3D printing. So in some cases, they've used very highly biocompatible materials. They've used materials like, again, like I said, titanium, etc. In that space, titanium, zirconia, etc. are being used, again depending on the expenses and all that. But when you're talking about using bioprinted parts, we should know that these materials are actually biocompatible or very nature bound materials. So getting that will be hard unless we've properly blended it with materials which can provide that much amount of strength to hold so much forces which have been done by our lower body, or so basically our lower jaw. So I hope this answers your question. So, and honestly, this is a very vast topic. So and there are very different sections of entirely recreating bone, in terms of what part of the body you want to create. So the complexities and the nature of the work depends on that. So I hope this answers your question, Shivani. And I guess we have ended this session. Okay, I see one last question. I'll just answer this. Okay, so for bone regeneration, we definitely like the idea of cell incorporated scaffolds, but it is also very hard to carry out the process. Say you are doing it in one particular stage, reproducibility is a very hard part to achieve. So having reproducibility requires extensive amount of skills, the right amount of facilities, etc., to kind of bring that on a larger picture. But I would definitely be more interested in, or I honestly feel that cell based is better. But there are also work done on cell free implants or cell free bone scaffolds which have been used. So the idea of 3D bioprinting again is to add cells, use cells. So that is definitely something that everyone is looking forward to. But if it is preliminary research, then you can go with without cells. All right then. I think I will end this for now. Thank you so much for joining us, and I'll see you again. In case there are some questions I've missed, I can definitely address them later on. Until then, thank you so much. So, kindly share, like, subscribe, visit us on our Altum Technologies website on LinkedIn, and please spread the word and also join us in upcoming sessions. So, thank you so much. I'll see you again.